Hi everyone, we are going to talk about 12.2. It is the one section on the AP test this year that we have not covered yet. And it's about transforming to achieve linearity. And our EQ is, how do we transform non-linear data and find and analyze its least squares regression line. Alright, so we know this because you've been in Algebra 1, Algebra 2, Pre-Cal, but not all data is linear. So how can we transform the data to fit a linear model? So remember that when we talk about linear and finding a linear model, and we talk about correlation and causation, and we find the R, the correlation coefficient, and all that, remember that correlation does not equal or does not prove causation. This is a reminder of something that you want to be aware of, that when you find it, you don't say, well, this proves that there's a relationship between X and Y. No, it shows that there's an association, there's a correlation, but it doesn't show that X causes Y and things like that. So power models are going to be the first type, and this is going to allow us to cover a lot of things, because think about all the different functions that you looked through in Algebra 2 Pre-Cal that are of the form x to the p. That would be x squared, x cubed. So quadratics and cubics are included in this model. So power models have the form y equals ax to the p. This describes the relationship of x and y. However, there is a linear relationship between x to the p and y. So if you think about it, if this was our whole variable here, then it would just be y equals, and we could call, say, make it z equals x to the p or something like that. So then you would just have y equals a z. Well, that's linear if this is our new, because we now have a variable of the power 1. And so you can think about it like that, or you can look at the linear relationship between x and the p root of y. And so if we were to take the root of this, then you'd also see a linear relationship there. Now, power doesn't cover everything, so we can also transform using a logarithm. Okay, and this works with when the data can be described by a power or by an exponential. So this is nice because it covers more ground. And so we will rarely use this unless they tell us to find a power model for it, because for the most part, this will end up taking care of power or exponential. So when you have this, you'll apply the log to both sides of the equation, so to both variables, and then you don't have to decide which method to use if you're going to take the raise y, or take the pth root of y, or raise x to the p. You don't have to make that decision. If you just take the log of both sides, you don't have to look and decide between those two. Alright, so here's an example. So if I take the log of y, and then I take the log of ax to the p power, well, then I can use my rules when dealing with logarithms to simplify this. So this would be the same thing as saying log of a plus log of x to the p, because remember that multiplication within the log is addition of the same base. And then if we have a power p, we can pull that out in front. And so now we have log of a is plus p log of x. Well, now this is a constant. That's a constant. Here are our variables. So now we have a linear relationship between the log of x and the log of y. And this would be like when we have it of the form y equals, or y hat equals a plus bx was the form we used this year, right? This was our constant, our y-intercept, and this was our slope. Well, this p is now our slope. So it has a p as the slope. Now, if you was dealing with an exponential problem instead, you would just have y equals a to the bx as our parent function for exponentials. And so we would take the log of both sides. You could also take the natural log of either side. This would work. I just modeled it using the log. but if you did it to the ln, that would also work. And so you have log of y equals log of a, b to the x, and then it's the same process of changing the multiplication to addition and the power to multiplication, all right? So there is now a linear relationship between x and the log y, and now log of b, this is now our slope, okay? So using any of these methods, you must then analyze how well they fit the linear model by using your calculator to find the r in r squared, okay? So your correlation coefficient, accounting for the variation. All right. So when you type in your data, let me zoom out a little bit. You can calculate the least squares regression line. Okay. And then you have to look at the residual plot. Now remember that a residual is how far the data point is from the line, right? And so the residual plot would just be the graph on your calculator that shows you the distance. And whenever you type in menu 47, it ends up turning it like it just plots a positive or negative. So this would be a positive, negative, and so on and so forth. All right. And remember that we said back way in the fall that if there was no pattern, then that meant that we could do a linear model. But if we saw a pattern, then that meant that it wasn't a linear model, that there was a pattern there that we could see that a different line, or a different equation rather, would do a better job of explaining. Okay, so if you see no pattern, then you can just go ahead and use your linear model. If there is a pattern, it's not just scattered, and we're going to look at some examples down here, then you're going to transform the data. Power model would be, you can take the log or natural log on both variables. Exponential model, you can do the log or natural log of y variable on the y variable, and the other options are like this. But for the other options, are you could take the square root of one side, or like the nth root. You could change it to a rational. And this is going to be a trial and error. You're looking for which one's the best fit, and you don't know which one's the best fit until you play around with it some. So kind of the method you'll choose is based on what the graph looks like or what the type of problem is. So if you know that it's a power, which is ax to the p, so it could look like this. It could be part of a cubic, or so it just depends. Like you're looking to see what would make it the best fit, and you can play around with your calculator whenever you're looking at the plot, your scatter plot. You can play around with the menu, analyze, and then play around with the different functions on there to see which one does give the best fit. And so your transformations is you'd raise the x values to the power of p, or you can take the pth root of y, or you can take the log or natural log of both sides. And if you do this, then you don't have to worry about these decisions. So for the most part, we'll just use this here. And I did want to show y'all on the calculator what it looks like whenever you go in and if you want to transform your data. So if you're looking at, you have like a x and a y, and it just says rad and y. It doesn't really matter what it says on here. But let's say that you want to just transform your y values, then you could do whatever your column is. You type in the equal bar, which is the second row here, b, and then your closed brackets to show that you want the b column, and then raise it to the cube power. Now if you wanted to take the natural log of each side, and so make sure that you're putting something that it doesn't automatically give you an error message. So then I could do equals, and then I would type in b here, and then because I want to take the natural log of that, I should have put natural log here. So that would be control here, and now I have the natural log, and then whenever I go to my scatter plot, I can pick which one, and I named that one LNY, if you remember. And so this is what the natural log looks like whenever that scatter plot is graphed. And so you can see that there's no relationship there. It's not a linear relationship, and my residual is on here, but if I wanted to take the residual off, that way we could show it again. So here's what x versus the natural log of y looks like, and you could also transform x so that you could look and see if you transform both of them, what would happen. But then if you want to see the residual, remember that you hit menu 4, 7, and then 2, and it's so far off that the residuals are beyond negative 0.8 and 0.8, so it does not manage to capture it. And you can look at what remember it's menu 4, 6, 2 is the line that goes through it, and I don't even see it. Let me see if I can zoom out to fit my data. That might be, nope, it's the line. I don't know where my line is, but okay, it's all the way up here. It is so far off that it's not even showing up because my data is just, I made it up, and so there's no relationship, and so there is no correlation. All right, now if it's exponential, then we have y equals ab to the x is the form it takes. And so remember that you have exponential growth and exponential decay. And so you could look and see, does it start off slower and then grow? Versus these, they kind of all have more of a curve constantly. And so then you could take the log or natural log of the response variable, that would be y. And then this is used for biology and money problems. All right, so that will wrap up these notes. I'm going to do a couple more examples in a separate video, but that way you can do it at separate times.